So any questions? Okay, so today I want to discuss two observations. The first observation is the night sky is dark. And the second observation is that if you look on sufficiently large scales, the universe appears homogeneous and isotropic. These assumptions of homogeneity and isotropy are the assumptions that really inform the idea of using Einstein's equations to describe the geometry and dynamical evolution of the universe taken as a whole. So these assumptions are really central to the whole subject of cosmology, and we'll see how to justify these particular assumptions. Okay, so the story begins with Thomas Digges in 1576, and his observation was rediscovered by Heinrich Olbers in 1826. And for some reason, Olbers gets the credit. Sometimes the guy who discovers something is ignored by historians who assign names to things. That's just how it happens, unfortunately. So the observation that these guys made is the night sky is dark, which is completely obvious, but the paradox they proposed is that it shouldn't be. So the way they argued it was that, suppose we consider a function f of r, which is luminosity over 4 pi r squared. So the rationale behind this function is numerator is the average luminosity of a star, and luminosity is the rate at which we radiate energy, so it's basically a power. And the denominator, 4 pi r squared, well, 4 pi, because you're radiating in 3 space, the light can go in any direction, and the light falls off as the inverse square of the distance. So that's the rationale for the 4 pi r squared. So this is basically the flux received. On Earth. So Thomas Digges was a fellow who translated Copernicus into English, and he noted in Copernicus that so Copernicus, in his heliocentric model of the universe, Copernicus had a sphere where the stars live. So Digges relaxed that assumption that there's a sphere where the stars live, and he said the stars are at every distance from us. So what these guys then did was, since this is the flux received, and we have an infinite universe maybe, we define the intensity, which we'll call dj of r, as the flux received from a particular star times n, which is the number density of stars, times r squared dr, since that's the measure we use for integrating in spherical polar coordinates. Okay. So the integral is j, and this is the integral from 0 to infinity dr, r squared times n times f of r, which is L over 4 pi r squared. So these r squareds will cancel, and we get 1 over 4 pi times n times times the integral from 0 to infinity of dr, which is infinite. So the conclusion is that because stars are every distance, every line of sight ends on a star, we get, as the intensity, infinity. So the night sky, and the day sky for that matter, should be infinitely bright. So let's try to disentangle the assumptions that went into this, this derivation. So the first assumption, maybe, is that we have an unobstructed line of sight to every star. We know that assumption is probably false because the sun has a radius, and therefore, because the sun obscures stars behind it, other stars should obscure stars behind them. So we don't have an unobstructed line of sight to every star, but every line of sight ends on a star. Okay? So this means that the sky shouldn't be infinitely bright, it should just be as bright as the average star. So it's not dark. That's the statement. So Olbers, when he tried to resolve the paradox, had a way out. His way out was dust. So there's interstellar material that absorbs starlight. And he thought because this interstellar material is absorbing starlight, this means the sky isn't infinitely bright. So what's the problem with that assumption? Yeah?
But that will heat up until it starts radiating the same.
Exactly. So the dust, because it's absorbing starlight, will eventually heat up, and eventually will have the same temperature as a star, and consequently it will start to glow, and it will emit at the same temperature as a star. So it's not really a way out. So another assumption was this number density n and this luminosity L are independent of R, the thing. We're interpreting it. So we pulled the n and the L out of the integral. So there's an assumption there. Number density n and average luminosity L are constant throughout the universe. And in particular, are independent of R. So the product NL has to fall off faster than than 1 over r, for the integral to be finite. If this integral, if n and L fell off like 1 over r, the integral of 1 over r is a logarithm. Logarithm of infinity is still infinity, so that would still be infinite. So if it's falling off faster than 1 over r, you can render this integral finite. Okay. So this assumption is plausible if it turns out that stars that are very, very far away, for whatever reason, turn out to be less numerous than stars that are nearby, or dimmer than stars that are nearby. If you're looking at distant galaxies, their stars seem to be as bright as stars nearby. So this isn't really the resolution paradox either. Another assumption is the universe is infinitely large. If the universe had a finite size, then J would be n L r max over 4 pi, rather than n L over 4 pi times infinity. That's a way to make J smaller. Another assumption is the universe is infinitely old. If the universe had a finite age, the most light we can get is the speed of light times the age of the universe. That's as far as light can travel in the lifetime of the universe if the universe has an age. So this is then R max, and J looks like N L C T0 over 4 pi. And finally, the last assumption that went into this argument was the flux is proportional to 1 over r squared. Now, this assumption is perfectly fine, but it's secretly Euclidean geometry that underlies this assumption. If the universe was curved and Euclidean geometry didn't apply, then maybe this is the wrong function. Also, in an expanding universe, for example, light is redshifted. So as light's redshifted, it loses energy. So that's another reason why this assumption would be false. So far, we don't know whether the universe is infinitely large. We know the universe began 14 billion years ago, so it's not infinitely old. And we know that in Einstein's conception of gravitation, geometry is curved. So the Euclidean geometry assumption needs to be looked at carefully. Okay? But of all of these effects, the dominant effect in explaining why the night sky is not bright is this one here. person to realize this was Edgar Allan Poe in 1848. Yeah.
Does that mean that one day the sky will be bright when the light from the ends of the universe approaches us?
I think it would take a very long time for that to happen. And before that happened, other effects would start to appear. So in particular, what happens is that the universe is expanding, and the expansion is accelerating. So we'll see this later on in the course, but what this means ultimately is that only things that are gravitationally bound will remain within our horizon. Everything else will fall out of the horizon, and we won't be able to detect those things anymore. So effectively, the thing which we're gravitationally bound to, the largest thing we're gravitationally bound to, is the Virgo supercluster. Anything bigger than the Virgo supercluster will eventually fall out of our horizon, so we won't be able to receive light from such things anymore. So the Virgo supercluster is big, but it's not infinitely big. So as a result, the universe will never, our sky will never be that bright. So one of my senior colleagues actually is rather distraught that the universe is constructed in a manner such that things will fall out of our horizon. And the reason he finds this disturbing is that this sets an upper bound to the complexity of life. You can't have life more complicated than the Virgo supercluster because everything else is going to fall out of our horizon. And this disturbs him deeply. So the scale at which you should worry about these things is the trillions of years. The universe is 14 billion years old. These issues don't manifest for a very long time. Okay, other questions? Okay, so the second point I want to make today is the universe is a fluid. So if you look, for example, at the microscopic structure of water, you'll find molecules. These molecules are all bouncing against each other, and there's molecular physics you need to understand the mean free path between these different molecules, and the dynamics of collision affect what's happening locally if you inject some other molecule bouncing around these water molecules. But if you look on large enough scales, the fact that water consists of these individual molecules doesn't really matter. There's an approximation in which we can think about the water as a fluid. And we can think about the dynamics of the fluid as describing whatever problem we're interested in. So if we're considering the behavior of a boat in the ocean, we don't really care about the molecular structure of the water in the ocean. We care more about what the boat's doing in the sea. So if you go deep enough into the water, it looks the same in all directions. There's nothing to distinguish one direction from the other. So on large enough scales, this water is a homogeneous fluid, and as well, it looks the same in every direction, and that's what's meant by isotropy. So the fact that the universe has the same properties of homogeneity and isotropy on sufficiently large scales means that, in some sense, the universe is a fluid, and we can use the dynamics of the fluid rather than worrying about what each individual galaxy in the universe is doing in describing the structure of the universe as a whole. So, this is called the cosmological or Copernican principle. Also the principle of mediocrity. We are nowhere, and we're nowhere special, and we're nothing special. So it's a fact which is in some ways reassuring. So isotropy is the statement that there's no preferred direction in the universe. Now you can say, wait a minute, the universe is expanding. You've said that multiple times. If the universe is expanding, it must be expanding from somewhere, and that somewhere it's expanding from has to be special. But the thing is, the universe is expanding as it appears to any observer in the universe. It's not a statement about us seeing the universe expanding. It's any observer in the universe seeing the universe expanding wherever they are. So the conclusion of isotropy is if there was a Big Bang, it didn't happen somewhere at some time. It happened everywhere. So isotropy tells us we can point the telescope anywhere. And see the same physics. Homogeneous means there's no preferred location in the universe. So not only can we point the telescope anywhere, we can put the telescope anywhere. So our friends in a classroom in a distant galaxy who were discussing the foundations of cosmology are having the exact same discussion. The universe is isotopic, the universe is homogeneous, and their telescope, which is looking at the universe in some direction from wherever they are describing the same physics as the physics that we encounter here. So, just like the fluid, these statements are only true at large scales. So if you're looking at the fluid on scales where you're sensitive to the mean distance between individual molecules, these statements aren't true. The universe doesn't look the same in every direction. Some directions there may be fewer atoms in other directions. So these statements are true on large scales. And these large distance scales are essentially distance scales associated to large superclusters that we encounter. So when distances are bigger than 100 megaparsecs, if you're looking for structures that extend more than 100 megaparsecs, then it's true that the universe is isotropic and homogeneous. There's no difference, for example, in the density of galaxies, whichever way you look, when you're looking on scales that are bigger than this. So, clearly, these assumptions by isotropy and homogeneity, they fail at short distances. So on Earth, there's preferred direction. We call it down. In the local group, there's a preferred axis. So the two biggest galaxies in the local group are our own galaxy, the Milky Way, and M31, Andromeda. Andromeda is slightly more massive than the Milky Way. But these two galaxies, they form an axis. And this is a preferred direction in that other galaxies are attracted to the more massive Milky Way and Andromeda. So here we do have things aren't the same whichever way we look. So superclusters are on the scale of 100 megaparsecs. And roughly every supercluster looks the same. Okay. Similarly, the average density of the universe, so density is mass per volume. The average density of the universe today is rho 0 is 3 times 10 to the minus 27 kilogram per meter cubed. Whereas in the solar system, if you measure the average density, it's about 10 to the minus 5 kilogram per meter cubed. And if you look at the local group, the average density is 10 to the minus 26 kilogram per meter cubed. So if you're looking at sufficiently large scales, then there's a lot of empty space and the density drops. Whereas in the solar system, there are things like solar wind, there is various there are particles you measure in any cubic meter of space that you collect in the solar system. Similarly, in the local group, there is an interstellar medium, intergalactic medium, and all of these things give us some density in empty space in the local group, whereas its average density, if you look at the universe as a whole on very large scales, drops significantly. Okay, so what do homogeneity and isotropy look like in the universe as a whole? So firstly, homogeneity does not imply isotropy, and isotropy does not imply homogeneity. So you can have things that are homogeneous but not isotropic, and things that are isotropic but not homogeneous. So as an example, you can imagine something like this. Here, if you average over scales bigger than the width of one of these bands, then it appears homogeneous. But it's certainly not isotropic, as there's a preferred direction. Okay? So this is homogeneous on large scales, but not isotropic. imagine something like this as well. This is isotropic from the middle. So if you're sitting here, any direction you choose looks the same as any other direction. But it's not homogeneous. Because, for example, this band here could be thicker than the other bands. Okay? So it's not homogeneous, but it looks the same whichever direction you choose to look. So our universe happens to be both isotropic and homogeneous on sufficiently large scales. You can also imagine things as neither homogeneous nor isotropic. That's easy. Okay. So, isotropy at every point in the universe implies homogeneity. Okay, so why are these statements relevant? So we believe the universe has a scale, and the scale is a function of time. Okay? So A of t is the scale associated with the universe. And we denote t0 as today, and A of t0 as A0, or the scale factor today. So because the universe is homogeneous and isotropic, we can say that the scale factor, whatever it happens to be, is a function only of time. It doesn't care about r, doesn't care about what angle you're looking at, so theta and phi are irrelevant. It's just a function of time. Okay? So we can study the dynamics of A and this describes the history and evolution of the universe. Okay? So that's the central simplifying assumption to the universe is both homogeneous and isotropic. We can just study dynamics in terms of time. Now, you can ask, why is it that time is being singled out? Why is it that we're not having isotropy and homogeneity in all the areas? And this is sort of what motivated the steady state idea of Bondi and company, that the universe should be isotropic and homogeneous in time as well as in space. So they were trying to extend the Copernican principle to apply to time as well, so that it's not just that there's no location, no direction that's special, there's no time that's special either. It turns out that time is special, at least as we can see the universe today. And the direction of time is one that behaves differently. You know, we can only move forward in time, whereas we can move forward and backward in all the other directions that we encounter. And there's a thermodynamic error of time, in that there's this notion of entropy we associate to the universe. This entropy is increasing as a function of time in any dynamic process. Okay, so time is special. Now, this is So why is time special? That's a natural question to ask. And the best answer we have is the second law of thermodynamics, which describes the arrow of time, is a statement about initial conditions, rather than a statement about dynamics. So for whatever reason, the universe started out in some state which was highly ordered. And as time evolves, it becomes more and more disordered. So that's sort of the best explanation we have for why there is this arrow of time. Yeah?
What does this order of the universe mean?
Okay, so you can imagine that the universe is in some particular quantum state. Okay? So suppose a quantum state of the universe was such that it was unique. Then that quantum state has an entropy associated to it of 0. Entropy is a logarithm of the number of states. There's one state, the logarithm of 1 is 0. So the entropy is 0 initially, for whatever reason. As time evolves, there become more and more states to which this initial state can evolve. And this process of finding a bunch of states to which the initial state can evolve is what we describe as the increase in entropy with time. So, for whatever reason, the universe was in a well-ordered state initially, and the configuration space of possible states increases with time. That may be natural if the universe is expanding. There are the reasons to think that a state with some density of matter concentrated here is one state, and some density of matter concentrated there is some other state. But these two states are not distinguishable because there's no preferred direction. So there are more states as the universe expands. We also know that the entropy of the gas, for example, increases with volume. So it's extensive. So as the universe expands, there are more states because of this extensivity of entropy. So, that's a reason why this entropy can originate and be concurrent with motion forward in time. Why is it the universe began in a low entropy initial state? We don't know. Because that requires us to understand the Big Bang, and we don't have such an understanding. Finish at 1:15, right? So we'll start to motivate Hubble's law. So this is Einstein's biggest blunder, he called it. He failed to predict the expansion of the universe because he assumed that it should be static. And the equations that he wrote down suggest the universe is either expanding or contracting. If you believe the equations, you would have predicted what Hubble found. What Hubble did was he took galaxies that were nearby. This was after this Shapley-Curtis debate was settled, and people decided the galaxies were outside the Milky Way rather than nebulae inside the Milky Way. He looked at these galaxies nearby, and he measured the relative motion with respect to our galaxy. And he found that all the galaxies nearby were, well, almost all the galaxies nearby were moving away from us. So the galaxies nearby, they're attracted to the Milky Way, so some of those galaxies nearby are moving towards us because of gravitational attraction. But if you're looking at galaxies that are sufficiently far away, they're all moving away from us. So we'll describe how he measured their velocities, but he found that there was a phenomenological description of how fast they were moving. So he measured the relative motion. He also measured their distance from us. measured the speed of relative motion and the distance, and he found that the equation describing the velocity is such that the proportionality constant that multiplies the distance to that galaxy. We now call this proportionality constant the Hubble parameter. So I'm deliberately not saying this is the Hubble constant, because it turns out that it's not a constant. It's a function of time, but its value today is h0. And the value of h0 that we measure is roughly 70 kilometers per second per megaparsec. So this actually presents rather a quandary, because it turns out that different measurements of h0 are slightly different numerically. So we've noticed this only this year, so it's quite a thing to figure out in cosmology. There are two different ways of measuring this. One way is a direct measurement, like Hubble made. That gives us 73.52 plus or minus 1.62 kilometers per second per megaparsec. And the second way of measuring this is looking at the cosmic microwave background and modeling that. And that gives us 67.74 plus or minus 0.46 kilometers per second per megaparsec. Now, if you look at the units of h0, it's a distance per time per distance. So this is 1 over time. So on dimensional grounds, the age of the universe is something which scales like the inverse of the Hubble parameter, as measured today. So these discrepancies in measuring h0 today are really discrepancies in stating what the age of the universe is. Okay? So this gives different ages of the universe. And we'd like to know how old the universe is. So that's why this is an interesting and important puzzle. So next time, I'll discuss how to obtain the Hubble law. And